Hey there, thanks for listening in and welcome to another Ellipsis Drive Podcast. Here we dive into the stories of people, companies and technologies that transform and empower spatial data-driven industries. My name is Rosalie van der Maas and today we have Adithya with us, calling in from Bangalore, India. Adithya is co-founder and chief product officer at SkyServe, and a very warm welcome to you.
Thank you.
Thank you, it's great to have you. Could you grab a couple of minutes to introduce yourself a bit further? Your background, role at SkyServe, tell us all about it.
Sure. So my background is not from geospatial, so that's the first part. So I come from the aerospace sector. So I have been building satellite systems, and then got into spatial data specifically because we were working on a lunar mission where we needed to deal with elevation maps, high resolution data from NASA's orbiting satellite that was mapping the whole lunar surface in great detail because there is this Artemis program coming up. They needed to figure out landing sites. So that's actually my introduction to spatial data. And a lot of tools were not really in, how would I call it, web-hosted form. So that's a lot of desktop applications. So you can guess ArcGIS, QGIS, and there are some custom workflows that we built. And that was the sort of trial by fire introduction to spatial data. And around 2019, that's when some of my colleagues and I moved out of my previous organization thinking there's something that we can do with the knowledge that we've gained, especially the intersection of spatial data, satellites, and look at the moon. Of course, it's really interesting. We're trying to understand a lot about our past in terms of how humanity got here. But looking at Earth really is a big problem. And there's not enough people doing what's necessary. So there's a lot of events, both man-made as well as nature's reaction to that. So we thought, let's bring this past experience to bear on the problems on Earth and use some of this space technology to capture what's happening on Earth, help folks who are actually on the ground making things happen. So that's the genesis of SkyServe. And from the name, this is actually not something that we thought about too much, but over time it's come that we want to leverage the skies or any assets in the skies to answer questions on Earth. So the core of what we're doing is to bring technologies such as edge computing and low latency communication to Earth observation. And while we're doing that, there are a lot of technical challenges that need to be solved, and we're doing them one at a time. And it's a very different paradigm of taking spatial data when it's on the satellite, converting that into something usable, and bringing that down in a way that somebody could put it on a map. And so my role at SkyServe is, as Chief Product Officer, is to find ways to package this technology in a way that users can leverage without too much of training. Though there is a lot of training material that we've created. In retrospect, it's always very easy when you start off, and as you start scaling up, you realize, okay, there is a lot of specialist domain expertise that you need to put out to your users. So it's mostly commercializing the tech that we've built with compute that can be run on satellites. I think we can speak more about what we're building as we go along.
So first a question around the product that you're putting out in the market. Like if you were asked to put it as simply and as plainly as possible, what is it you're selling or looking to sell?
So we are selling capacity on smart satellites, some of which are already flying in space. And that capacity is not just sensing capacity, it's sensing plus compute. We're giving that access to users to leverage that to solve their business problems or probably national government problems using this as an infrastructure.
And the satellites you're currently offering the service with, they're managed by you, or they're managed by partners that are the operators of the satellites themselves?
Yeah, so it's internally for us at SkyServe, it's a very important question. So we initially started with a sort of blank slate. If we need to bring this capability to bear into the market, we could build our own satellites, we could put the sensors, we could put the compute. But then we quickly realized that the scale at which the problem has to be solved, you cannot build every single satellite. You can't really build the best sensor for every single use case. So that's where we are partnering with folks who are putting out single satellites, satellite constellations, as well as those who are building many complementary technologies. So what we do is we place either compute hardware onto these satellites, or we build a software that can run on any compute that they can give. As long as that compute is not the brain of the satellite itself, there's a secondary compute system available. So that is not so critical, but it's crucial to leveraging data where it's being generated. So that's generally been our approach. We don't build the whole satellite, but we partner with folks bringing these into the market.
Okay, then that's very clear. And then indeed, you are in the market to partner a lot, I imagine, then with all the hardware that's going into space. There's plenty of opportunities there. But let's focus on your mention of low latency. Like, the real time element is a very core part of the value that you bring into the market, with what you're looking to deploy on satellites as well. So can you give a bit more color to this, or a bit more context around the importance of that, and perhaps give some context with some of the missions that you've been part of lately?
Yeah, so I can give an analogy, something that we've already seen happen on the ground. So my example is the speed cameras on expressways. So they are essentially sensors, and sometimes they are more than one thing. It's not just a camera, it could be even a speed radar, it could be some sensors on the road. But the expressway patrol is not located everywhere where there could be a violation. So they are probably in a control center far, far away. And you have the sensors which need to detect violations of speed, probably changing lanes, aggressive driving. So sensors need to pick that up and probably even take action very quickly. So either they can warn these drivers, or they can directly lodge a ticket against the license plate number. So what you see here is there's processing needed very, very close to where the sensing happens, and connect that to an action, or at least notification to another entity that can take action. So this is very, very, very close to what we're building, where you need to take action. The satellite goes very, very far away from us, but also the incidents that really happen, say out at sea in the middle of a cross-country pipeline. It could be forests in the middle of a drought-stricken forest. There are no people there. And the key part is to detect that remotely with satellites, and also communicate that back probably to first responders as soon as we can. So this is the definition of low latency. Real time is something that I guess is more aspirational to us. We'd like to get as real time as we can. And if we relate that to the mission that we did recently, which is our Matterhorn. So this is with a partner called D-Orbit, based out of Italy. And they had a satellite that was launched, I think 2 years ago. And it had a camera, not really great resolution. And it had, I think, a technology demonstrating edge computer on board. So these were launched with the specific purpose of just testing those pieces of hardware individually. So the camera was supposed to take a few images, and then the manufacturer basically says that this is space grade, this can work for more satellites. The edge computer went on its first flight to demonstrate that you can compute with, say, a vision processing unit or a VPU with multi-core CPU in space. Usually you don't put that amount of compute in space. So what we planned to do was to leverage some of these satellites which have some capability, reprogram them to demonstrate something that it was not originally launched for. So that's where we started speaking with D-Orbit, I guess, sometime in December last year. We completed the paperwork in March. We sent up the software on April 2nd. And few days after that, we were able to demonstrate this. So it's pretty quick. And the key capability that we're trying to put together is that if satellite operator and their hardware are agile or software defined, you can make those satellites do a lot of things that probably you didn't even imagine it could be capable of. So in terms of the low latency, so it's under a minute from imaging a location to returning a result of processing on board down to the ground. So that's a very controlled test. So that's a disclaimer. So there was a ground station very, very close to where the Earth was imaged. So you could demonstrate compute transmit very, very quickly. But if this had to be done for any other part of the world, you would have to leverage some new technologies like inter-satellite communications. I think Starlink is providing this. Now there are many geostationary telecom satellites as well that can give you this connectivity wherever you are, either on the Earth or in space. So these are technologies that we will slowly start integrating, and it requires the partnership of everybody, both in space as well as on the ground.
Partnership remains keyword, but I see why for sure. But so that's under a minute. How does that compare to the status quo today?
So the most I would say bottlenecked part is actually getting the data to the compute, and because compute was never really factored in on satellites, so the compute could not start till the data comes down to ground. And this is proportional to the size of data. So if the swath is large, the resolution is really fine, then the file size is like humongous, and you don't really prioritize bringing down important images because there is no context of important images on the satellite. So it is not designed to know what it's imaging, right? So if you've taken probably a long strip all the way from the south of Africa to, say, Egypt, and there was fire somewhere in between, so say north of Nigeria had a fire, you would start transmitting the images starting from Cape Town and end with the images of Egypt. And once you start processing them, that's when probably a few days later, you'll discover, okay, there's a fire in the north of Nigeria. So if you had to just prioritize important events, you would have to take that decision even before the data came down. So that's a sort of difference that you would see with edge computing.
Got it. That's a nice example to the analogy that you made earlier with the speed cameras was a nice one as well. So you mentioned fire. What are other expected use cases, or what do you focus on in terms of applicability here on Earth?
So there are probably far more than I can list, and I myself won't be able to come up with all the applications of this. And this is the beauty of Earth observation data. I think the use cases are infinite, and we're all the time just touching the tip of the iceberg. So fire is something that's come up. I think there are even competitions being opened up. I think the XPRIZE Wi-Fi Challenge is bringing this out. They also have a space-based detection and tracking component to the challenge, which says use satellites in real time to detect and report where fires are. So that is something that is certainly at the top of what we're concentrating on. There are others which are related to human interference in the way nature works. So there's methane gas emissions, which if you can detect them early enough, especially in remote locations, you can mobilize fast enough. But if you have gas leaks in populated centers, people on on the ground itself will pick it up. There are lots of trace gas sensors in every weather station, so they will pick it up. But if it's a cross-country pipeline where there's little to no habitation, it will not get picked up because you cannot sensor, as in you cannot have lots of sensors everywhere. There's also the other part, which is I think Global Fishing Watch actually brought this out. And even there, in their map, you can see there is no detection of illegal fishing, I think 50 miles away from every coastline. There is a huge dark patch all over the world where there are absolutely no detections of any activity. But all maritime trade goes through that. You do not have persistent surveillance of that either from satellites or even on the ocean. You do not have any way to know that. This is another one, which is oil spills, illegal activity in terms of overfishing. It's also, it's only when you see it that you actually notice how many artificial islands are coming up. And this is not just a strategic use case, but it's also ecological matter, because you probably are displacing biodiversity in that region because of these artificial islands that you're dredging and filling up land. There's another side to watching the oceans, which is as of today, I think it's not getting enough attention, but there's a lot of garbage that's in the sea. It is flowing and it's flowing dynamically, and these affect the biodiversity as well. And we do not have to image them or to track them because you do not turn on any satellite when it's above the sea. So you see it with the Copernicus program, the Landsat program, even MODIS, even though the raw data actually has collections above sea, but any of the products that you use as an analyst, the sea pixels are removed. So there's a lot of technical challenges in actually looking at the sea. And this is one of the things that we are partnering with a few folks who actually want to build always on satellites, both in microwave as well as optical. So they will be on even if they're flying above the sea. And you can detect these as you go.
I think some of the other use cases you mentioned were also the ones that I would be thinking of when, near real-time insights from space are concerned, but I hadn't realized that monitoring the ocean would be a much more attainable possibility if you can indeed compute on board, because then what you send down won't be a set of useless pixels. So that's good. It's very interesting. So in delivering these real-time insights to end users, what are the hurdles that you're seeing, or how are you overcoming these hurdles for that last mile?
Yeah, so these are the early days. These are the early days of this type of technology being brought into space. And it's, I think, 2018, there was a conference organized by the European Space Agency on onboard data processing. So that's when this started. So this is pretty new. It's a very young technology. And the challenges that you face are typical of anything that is new. So educating the user is the most important thing. So while we try to do business and we try to introduce this new capability, oftentimes users either over predict what it can do or they undermine it for what it cannot do today. So this is one of the key challenges that we've seen, is educating the user. And there's another side, which is where the user is pretty clear, like say for wildfire detection. The assumption of anybody who's funding this requirement is that there are lots of satellites with the right type of sensor, which can be available 24 hours, 7 days a week without fail. So that assumption, if you actually try to go back and see what would have what should have been done in the past to make this assumption true, is you need a lot of satellites outfitted with probably thermal infrared, shortwave infrared sensing capabilities. You need a lot of satellites to be able to give continuous coverage. And just thinking of that, you'll be thinking as probably we're polluting space more than anything else. And the other side is the type of data that you can generate from all of this. It for sure, edge computing would help, but it doesn't necessarily mean that all these types of satellites that are being put up have parity in terms of quality. So one satellite may be capable of a very wide swath scan at low resolution, but with a very good radiometric quality. So if you're telling there's a 5 pixel, there really is a 5 pixel. But sometimes you have very high resolution and very small swath cameras, where because the pixel size is so small, the signal to noise ratio of picking up fire could be the same as, say, solar reflection on a solar panel, or could be glint from a lake, and which is still going to be registered as fire. So the quality of these are very, very different. And when you speak to folks saying, hey, this can be edge computed, the assumption is that you get the same quality as, say, the WIRS sensor, which is on one of the NOAA satellites, as you would get on a Maxar satellite. It's not the same. So the difference in work has to be done by somebody. Sometimes the first assumption is that we as SkyServe will do it. So that's a good proposition. If we know how to do it, okay, we can do that as contracted out consulting work. But if we can't do that, this assumption actually breaks down the whole use case. And this is another challenge which, when you introduce a new piece of technology, they feel all the other things can be forgotten, but it can't be. You still have to solve the same problems. So yeah, this is something that we've seen, and this approach of ours of combining capabilities and capacities across satellites, I really think is one way to solve this, and it needs to be demonstrated to really users to appreciate that if you can sense the same phenomenon using different types of sensors across different satellites, and you can sort of normalize the quality such that it's actionable. It shouldn't be that 9 out of 10 detections are false positives, right? So that's the key thing. That's where we are going. A lot of the technical work we're doing, trying to then make this data look the same, feel the same, process the same. And there's also a lot of efforts, I guess, so that OTC and many other standards organizations are trying to do, which is to define analysis-ready data. But that's a very different topic. Yeah.
Another topic, though, that is interesting to dig into some other time. Okay, so what is on the calendar for you guys for the rest of 2024? What are some milestones that you're looking to reach in this calendar year?
Yeah, so this year we have at the start of the year we had 2 missions planned, and then of course the one that we demonstrated in April happened out of the blue. So now we have 3 that should be done by the time we get Christmas. So there's one mission that's done. The second mission with a company called Loft Property. So they are France and US based, and they have a pretty special satellite with a multispectral and a hyperspectral imager with 2 different resolutions on the same platform. What we are planning to do with that is generate in real time a fused product which is defined by the user. So there's one imager that has a better spatial resolution, while the other one has better spectral resolution. And we hope to create a product on the fly based on what a user wants. So if a user wants, I want to characterize a specific metal sitting as ore on the port, and what's the best set of bands that can characterize that. If that is known, we can generate that product so that you're not using all the 100 or 150 bands of the hyperspectral imager, and you're not limited by the smaller spatial resolution of the hyperspectral imager as well. So you can sort of sharpen it to very close to the resolution of the multispectral one. So this is something that's a new technical capability, but we also have an intersatellite link on this specific mission. So we are going to demonstrate the ability to get back to the user over the internet within 5 minutes of any detection. So this was not possible with the first demonstration that we did, but here it can really be done. So these targets are possible. So we can detect illegal phishing because there's also a receiver on board. There is the possibility of detecting and reporting fire, no matter where the fire occurs. So these are two prime use cases that we'll be trying out. And also we're working with a few customers to fine-tune the methodology as per sample data that we get from the satellite itself. So there are new things that you can do once you see the actual raw data. And those are use cases that we'll be developing as we go along.
All right. Okay. So
we have another satellite as well that hopefully should get launched. So that's getting launched out of India. I think that's a multispectral imager as well. But here what we've done is we've taken a computer that's commercially available. We've modified it heavily to run natively for our software. So we have far more control on this mission. And that should launch in September, hopefully, fingers crossed, because a lot of launches are getting delayed out of India. So so that's the second one that we're looking forward to. So a lot of background work is going on.
Yeah, wow. So that sounds like there is a lot to check in on by the time indeed Christmas rolls around. And hopefully you'll be able to have hit all those targets. Okay, excellent. Great. So I am afraid, though, that with that we are at time. So on behalf of our listeners, thank you so much for sharing your story and your insights. And if you're tuning in and you'd like to know more about Adithya or about SkyServe, we'll leave some links in the description so you can find the resources you're looking for. And with that, thanks for being here with us today. And until the next one.
Thank you, Rose.